Welcome, everyone. Today, we are diving into one of the most fascinating and powerful topics in linear programming: hyperplanes and extreme points. If you have ever wondered how massive companies optimize their supply chains or maximize their profits out of millions of possibilities, the secret lies entirely in the geometry we are about to explore right now. To begin our journey, let us imagine a solid block of cheese. If you take a perfectly straight knife and slice completely through it, that flat surface created by the cut is what mathematicians call a hyperplane. In our daily lives, we are surrounded by these flat boundaries, like the walls of a room. In linear programming, every strict business constraint, such as a budget limit or a maximum labor hour restriction, acts exactly like this flat boundary, separating what is mathematically possible from what is impossible. Understanding this boundary is our first step. Now that we understand the flat walls, let us look at their mathematical form. This equation tells us that a hyperplane is the collection of all possible combinations of our decision variables that exactly use up a total value z. The variables x represent the decisions we need to make, like units of products. The coefficients c represent costs or profits. If any variable x increases, another must decrease to keep the total sum exactly equal to z, which is exactly why the surface remains perfectly flat. This simple linear relationship is the building block for all complex optimization models we will build. Now that we have our flat walls, what happens when they crash into each other? They create an extreme point. An extreme point is simply a sharp corner of a geometric shape, formerly known as a vertex. Imagine standing exactly on the sharpest corner of a triangular room. You cannot take a step in two opposite directions and still remain inside the room. These corners are created exactly where our hyperplanes or constraints intersect with one another, locking us into a specific position. This brings us to the formal mathematical test for an extreme point, using a concept called a convex combination. A convex combination is just a formal way of describing any point that lies on a straight line segment drawn between two other points, x1 and x2. The symbol lambda is a fraction between 0 and 1, representing how far along that line segment we have traveled. The formula states that a true corner point cannot be formed by blending or averaging any two other distinct points from within our allowed region. If it cannot be blended, it is a true extreme point. Before we move on, let us see this with a concrete example. Suppose a small bakery makes bread and cakes, having exactly 12 cups of flour available. Bread requires 2 cups per loaf and a cake requires 3 cups. We want to graph the hyperplane representing the use of all 12 cups. To draw this straight line, we find where it crosses our axes. First, we ask what happens if we bake 0 loaves of bread. Setting x1 to 0, the equation simplifies and we find we can bake exactly 4 cakes. This gives us our starting point on the graph. Continuing with our bakery, we now have our first point on the vertical axis at 0, 4. Next, we do the exact opposite to find the other end of our straight line. We explore the scenario where we bake 0 cakes, dedicating all resources to bread. Setting x2 to 0, we find we can bake exactly 6 loaves of bread. This gives us our second point at 6, 0. By connecting these 2 points with a straight line, we have successfully drawn our hyperplane. Every point on this line uses exactly 12 cups of flour. Now that we know how to draw a single hyperplane, let us find the extreme points for a complete system of constraints. Imagine a factory producing 2 types of toys. We have a machine time limit and we cannot produce negative toys. To find the extreme points of our allowed production area, known as the feasible region, we must treat our inequality constraints as strict equalities. This turns them into three boundary hyperplanes: the vertical axis, the horizontal axis, and the machine capacity line. These walls will define our shape. Let us find exactly where these boundary lines intersect each other. Our first extreme point occurs where the two non-negativity walls meet. Setting both variables to 0 gives us the origin, 0, 0. This means producing absolutely nothing. Next, we look at where the vertical axis intersects our machine time limit line. By substituting 0 for x1, we are choosing not to produce the first toy. Solving this gives us our second extreme point at 0, 4, dedicating all time to the second toy. We are tracing the outside of our region. Finally, we need to find where the horizontal axis intersects our machine time limit line. We accomplish this by substituting 0 for x2, representing a business decision to completely stop producing the second type of toy. This calculation gives us x1 equals 4. We have now found our third and final extreme point at 4, 0. These three sharp corners define the absolute limits of our feasible region and hold the key to finding the optimal business decision. We have successfully mapped out every corner. Let us look at exactly what we just calculated. Here is the visual representation of our factory's feasible region. The horizontal and vertical axes act as our impenetrable non-negativity walls. The slanted line represents our machine time limit. The hyperplane x1 plus x2 equals 4. The shaded gray triangle is the physical space where all our constraints are satisfied simultaneously. Notice the three black dots at the corners: 0, 0, 4, 0, and 0, 4. These are our extreme points. This beautiful geometric shape leads us to a crucial question. Why do hyperplanes and extreme points matter so much in the real world? In business optimization, a company might have millions of possible ways to allocate its resources. However, a fundamental mathematical theorem proves that the absolute best solution, the one that maximizes profit or minimizes cost, will always occur at one of the extreme points. Instead of searching blindly through infinite possibilities, a computer algorithm only needs to check these sharp corners. This brilliant geometric shortcut saves immense computing power and time. To summarize our journey today, we have learned that a hyperplane is simply a flat boundary representing a strict limit in our problem. When multiple hyperplanes intersect, they carve out a geometric shape, and the sharp corners of that shape are called extreme points. Because the optimal solution always hides at one of these corners, understanding how to find them is the absolute foundation of all optimization techniques. You now understand the exact geometric logic that powers the world's most advanced decision-making software.